Hello, my name is Xiangyu, and I'm glad to present our recent work about building a high-performance fine-grained deduplication framework for backup storage. Data reduction is already a widely discussed topic, and there are several kinds of approaches for different scenarios. General compression, like LZ series and deflate, is quite common for most users. And they usually detect and eliminate redundancies at string level. But this kind of approach only finds redundancies in a limited searching range, and thus the compression ratio is also limited. As a result, the major scenarios are Euro-sized files. Deduplication is proposed to handle the case of very large files, and it will separate data streams into chunks and remove identical ones globally. Although deduplication could detect redundancies far away from each other, its coarse-grained processing granularity sacrifices the deduplication ratio. Generally, both two kinds of approaches have been widely used in storage products, but they cannot fully utilize data's compressibility. Fine-grained deduplication is proposed to recover the lost compressibility of chunk-level deduplication. It not only removes identical chunks in data streams, but also eliminates redundancies among similar chunks. The left figure gives an example. The first and the third chunks are identical, and the second and the fourth chunks are similar. Fine-grained deduplication is to detect similar chunks for n duplicated chunks, and then read back a similar one as the base chunk. After that, delta difference between the target chunk and the base chunk will be calculated as the red figure, and to eliminate redundancies between two chunks. In this way, fine-grained deduplication achieves a global and string-level approach. This solution sounds great, but it suffers from some costs. Eliminating redundancies always lets compressed files share common parts, and this kind of data reusing will hurt locality. For the example in the figure, file 1 and file 2 both contain chunk A and chunk C. But in physically stored chunks, file 2 has a poor locality because its component chunks are not located sequentially. This example suggests a case of data reuse, and from that we could learn that data reuse always hurt locality. And fine-grained deduplication introduces a new form of data reuse compared with chunk-level deduplication. It is data encoding on similar chunks. Therefore, fine-grained deduplication introduces additional locality issues, and it will get performance of the deduplication and the restore workflows. And in this work, we aim to address these additional issues. The first additional issue is in the deduplication workflow, or we call it the read path. It is related to reading base chunks for data encoding. For the example in the left figure, we have two backup workloads for fine-grained deduplication. Backup 1 is first processed, and when processing backup 2, we learn chunk A and chunk C are duplicates, and chunk B prime and chunk D prime both have a similar chunk in backup 1. Then, we need to read chunk B and chunk D as base chunks. This example suggests how similar chunks are generated in common cases, and it means where similar chunks appear is actually decided by users' modifications. It makes the distribution of base chunks scattered and random for the storage end. Besides, consecutive deduplicated chunks are usually compressed together to further reduce storage costs, and it means accessing any chunk must be in a large unit. These two causes lead to bad results. For the example in the red figure, when we run delta encoding on chunk B prime and chunk D prime, we even have to read the whole container for only one base chunk. These are very inefficient I/O. We summarize this issue as poor locality in base chunks, and if base chunks could be more concentrated, the I/O efficiency could be significantly improved. The second issue is in the restore flow, and we could call it the read path. We observe that there are two kinds of reference relationships in fine-grained deduplicated data. The first is between backup workloads and chunks, and the second is between delta chunks and base chunks. The following figure gives an example. The green shaded chunks are directly referenced by the third backup, and the blue shaded chunks are directly referenced by their base chunks and indirectly referenced by the third backup. The second kind of reference relationship is additionally introduced by data encoding, and thus aggravates the fragmentation problem in deduplicated data. And because of the large I/O unit, when restoring the third backup, we have to read all the 5 containers, and it causes many unrequired chunks to be read. Therefore, we summarize this issue as poor locality in restore required chunks, and if this restore required chunks could be located more compactly, the I/O efficiency could be improved. The third issue is also in the read path. When restoring a backup, we need to traverse all restore required chunks to construct a whole backup workload. However, because of the dependency between delta chunks and base chunks, some containers will be accessed repeatedly. For the example in the figure, we restore backup N with its recipe. Several containers are used. Several containers are read in order to get all restore required chunks. Though all chunks in container 1 are required in backup N, we have to access container 1 several times because chunks in container 1 are used at time far apart. We summarize this issue as repeatedly accessing in restore required chunks. These 3 issues trouble both the deduplication and the restore workflow, and we propose 3 techniques for them respectively. Then, combining these techniques, we proposed a fine-grained deduplication framework Mega. It runs selective data encoding on the deduplication workflow, applies the data-friendly data layout on deduplicated data, and performs AFR traversing and delta pre-writing on the restore workflow. The first technique is selective data encoding. We observe that base chunks are not distributed evenly. For example, in an evaluated dataset, about 64% containers only hold about 8% base chunks, and we call these containers base sparse containers. This observation gives a hint that skipping data encodings whose base chunks are in base sparse containers will only cause a limited deduplication ratio loss. Accordingly, we combine several chunks as a segment and then count how many times each container is required for base chunks in a segment. If a container is required for 2 field times, I mean smaller than a threshold, it will be regarded as a base sparse container, and we skip data encodings whose base chunks are in this container. As a result, we can avoid reading inefficient containers and thus accelerate the deduplication workflow. The second technique is delta-friendly data layout. We consider the 2 kinds of reference relationship together and define the necessary chunks of a backup. It is a combination of backups directly and indirectly referenced chunks. And then we define the life cycle of a chunk according to backup's necessary chunks. Finally, we apply life cycle-based classification on deduplicated data to organize a data layout, as shown in the right bottom figure. In this data layout, restore required chunks of any backup are located compactly. For example, if we want to restore the third backup, cat13, cat23, and cat33 are all we need, and there will be no unused chunks to be these categories. Besides, the paper has more discussions about the evolution of this data layout to support saving more backups and deleting old backups. For the third issue, we proposed always forward reference traversing and data pre-writing. The always forward reference traversing is a special path to traverse the restore required chunks, and in this path, data chunks always appears before their base chunks. We found this path exists in the data-friendly data layout, and achieving that needs to follow several rules. In general, for all restore required categories, we need to access columns in positive order and access rows in reserve order. For example, cat13, cat23, cat and cat33 are needed categories for restoring the third backup, and according to the rules, we need to access cat33 first, then cat23, and finally cat13. Discussions about why this special path exists are detailed in the paper. Supported by this path, we could apply the data pre-writing mechanism by utilizing the asymmetric I/O characteristics of backups and user storage media. Like the example in the red figure, when restoring a backup, we traverse all restore required chunks when we traverse all restore required chunks with the special path, and when encountering a delta chunk, such as delta f prime, we pre-write this chunk to the offset of f prime in the to be restored workflow. I mean that f prime is the decoded chunk of delta f prime. Then we continue traversing, and when encountering chunk f, we reload delta f prime from the to be restored workflow and decode delta f prime to get f prime. Finally, we write back f prime to its offset. Besides, delta chunks also could be pre-written to a cache instead of the to be restored workflow as an alternative solution, because delta chunks usually only have quite smaller size than normal chunks. The total size of the cache could be quite small. The evaluation includes several approaches proposed or used in recent papers. There are 3 fine-grained deduplication approaches and 2 chunk-level deduplication approaches. 4 backup datasets are used for evaluation. These datasets represent various typical backup workloads, including website snapshots and open source code project, virtual machine images, and synthetic datasets. They have been used in several deduplication studies. The first is evaluations of the deduplication workflow, and there are 2 parts, including the backup speed and statistics about accessing disks for reading base chunks. Results suggest that Mega achieves a close performance to chunk-level approach and up to 34 times higher than Greedy. For selective data encoding, a higher threshold leads to a higher speed. Besides, the statistics about accessing disks for reading base chunks suggest that selective data encoding hugely reduces disk accessing times and avoids reading inefficient base chunks. And this is why Mega's backup speed is improved. Then we consider the deduplication ratio. Fine-grained deduplication approaches usually have a much higher deduplication ratio than chunk-level approaches, and the Greedy is the highest one. The VMS dataset does not have many similar chunks, and all fine-grained approaches do not achieve a much higher deduplication ratio on this dataset. The deduplication ratio loss caused by selective data encoding is limited, except the synthetic dataset. It is because modifications in this dataset are completely random and non-natural. Generally, Mega preserves a deduplication ratio advantage of fine-grained approaches. Evaluations on the restore workflow also have two parts, including the restore speed and the statistics about accessing disks for required chunks. Results suggest that Mega achieves up to 105 times higher restore speed than Greedy. And the statistics about accessing disks suggest why Mega could achieve such a better performance. On the one hand, the Delta-friendly data layout addresses the fragmentation problem and reduces the restore involved containers. On the other hand, always forward reference traversing and delta pre-writing significantly avoid repeatedly accessing containers. We learned that though repeatedly accessing issue also exists in chunk level deduplication, it is relatively slight, and the chunk level approach's main challenge is the fragmentation problem. And this is why we tend to consider the repeatedly accessing is a typical issue of fine-grained deduplication. Results suggest that other fine-grained deduplication approaches hugely suffer from these two locality issues, and Mega has a better I/O efficiency in the restore workflow. Finally, we conclude that this paper talked about the three additional locality issues introduced by data encoding and proposed three corresponding techniques to address these issues. Supported by these techniques, Mega achieves a significant performance improvement while preserving fine-grained deduplication ratio advantage. Finally, thanks for listening, and please feel free to ask me if you have any question.